In section 5, we're going to look at a new way of doing proofs called an indirect proof. Now before, if we looked at a direct proof, we're normally starting with some given information. From that given information we know something, and that leads to something else, and eventually we get to what we're trying to prove. But in an indirect proof, we're going to go about it a different way. What we're going to do is we're going to look at whatever we're trying to prove, and so we're going to assume the opposite of that part of it. Now then we're going to use what we know, using our givens, our postulates, our theorems, until eventually we're going to find a contradiction. If we prove the opposite of this, and so basically not something, then eventually we're going to have a problem because this can either be true or false. And so if what we assume to be is false, then whatever our assumption was, the opposite of that, or the something, has to be true. So we assumed not something was true. We showed there's no way that that could possibly be the case, and so the opposite of that, or the something, would be true. Okay, as an example of that, let's look at this proof. We want to prove that Thailand is not in North America. So we're going to assume the opposite. We'll assume that Thailand is in North America. Now, if Thailand is in North America, we're going to use what we know. Thailand is in Asia. Okay, but we're going to find a contradiction to that. Thailand cannot be in both Asia and North America at the same time. There's no overlap between those. And so therefore our assumption that Thailand is in North America, we have to take the opposite of that. Thailand is not in North America. So looking at our assumptions, we want to look at the assumptions that we need if we want to start an indirect proof of these statements. So if we want to prove that AB is not equal to MN, we prove the opposite. The opposite of equal would be not equal. If we want to start with PQR is an isosceles triangle, is not an isosceles triangle. If 9 is a factor of n, then 3 is a factor of n. So the opposite of that would be 3 is not a factor of n. Basically what we're looking here is we're looking at the then part. Remember, if would be given, while this would be our prove part. And so that's the part we want to negate or take the opposite of. Okay, now another important thing to look at is if you have something like x is less than 4. Now we could try to write that as something like x is not less than 4, but that's not a very useful way of looking at it. We want to look at it instead that x is greater than 4, but notice this doesn't really say the opposite of it because we're forgetting about the number 4. Is the number 4 less than 4? No. So we actually have to say x is greater than or equal to 4. Okay, so which statements contradict each other? So if we're looking for these for a contradiction here, say I've got these two segments are parallel to each other, congruent to each other, and perpendicular to each other. Now if I have parallel segments, they could also be congruent. But they cannot be both parallel and perpendicular. In this next example, we're going to use an algebraic proof. Now we're going to start by assuming the opposite. Remember, we always start with the opposite of the prove part. Now remember here that x greater than 5, the opposite of that could be x is less than 5, or it could be x is equal to 5. Now we could also write this as x is less than or equal to 5, but often with inequalities it's better to look at this in two cases. Now we're going to use what we know. We were given that 2x minus 3 is greater than 7. And we're going to look for a contradiction. Now what we're going to do is we're going to try any example from either one of these. So we'll start by using the x less than 5. So let's just choose a number less than 5, maybe the number 4, and we're going to use what we know. 2 times x minus 3 has to be greater than 7. If we plug in the number 4 though, that gives us 8 minus 3 greater than 7. That gives us 5 is greater than 7, but that's a contradiction, that's a problem. Now notice that only addresses the first part. We actually have to think of this in two parts. So next I'll look at the x equals to 5. Maybe that will work. So let's try 2x minus 3, but we're plugging in the 5, and it has to be greater than 7. Now this is going to give us 10 minus 3 is greater than 7, but that tells us that 7 is greater than 7. Now this is also a contradiction because 7 is not greater than 7. So we're getting a contradiction from both of our assumptions. Therefore, the only other possibility, if x is not less than 5 and x is not equal to 5, then the opposite has to be true. X is greater than 5. Okay, now in a geometry proof, it might look something like this. L is not parallel to M is what we're given. Now we don't have any rules or theorems about what to do. We're asked to prove that 1 cannot be congruent to 3. Now our theorems were always about if it's parallel then it's congruent, or if it's congruent then it's parallel. So we're going to have to use an indirect proof here. So the first step here, we're going to assume the opposite of the prove statement. Assume angle 1 is congruent to angle 3. Okay, because there's only two possibilities, either congruent or not congruent. Okay, now we're going to, using this information, angle 1 congruent to angle 3, then angle L is parallel to M, because if corresponding angles are congruent, then the lines are parallel. But we were given that L is not parallel to M. We should point out this is a contradiction. Therefore, we have to go back to our assume angle 1 congruent to angle 3, and we know that that cannot possibly be true. Now notice that we're writing this kind of as a paragraph proof, but we still, if you look closely at it, for each thing we have a statement and a reason. Okay, here's another example. We're given that we have a scaling triangle, and we want to prove that the three angles all have different measures. So the opposite of this could be that all of them have the same measure, or just that two of them have the same measure. Now since we're just looking for a contradiction, I'm only going to look at the contradiction of just having one set of them being congruent. Okay, so we have one set of congruent angles, and so let's draw a picture of this, and B with equal measures, and then C. Okay, now notice if I made these two congruent by the converse of the isosceles triangle theorem, we know that the sides opposite of congruent angles here would also have to be congruent. If the two sides are congruent, then ABC is not scaling. But this is a contradiction, because we're given the triangle ABC is scaling. Therefore, the opposite of our assumption has to be true. Now really I should have been a little more careful. I gave specific names to which ones are congruent. I should have just said two angles are congruent. And I could have done the same proof with B and C or A and C, but I still would have come to the same conclusion.